Well, it's at the hour now, so maybe we'll just get started then. You happy, Arthur?
Yeah, that sounds good. Let's go.
Okay. Hi everyone. Thanks for coming to see us talk. Thank you for letting us talk at this cool event. I really like the the system that we have here. It's worked actually really well for us. It looks pretty modern, pretty cool. It looks almost like a video game when you join. But yeah, my name's Philip, and Arthur's here as well. We're going to be talking to you a little bit about our project. So we're going to talk about Rust-GCC. This is we'll talk about what it is and what it's all about. But I just thought you might like to see the little logos here. So there's Ferris the crab, which some people might be familiar with, which is the mascot for the Rust programming language. And I spent way too long cropping the claw in half and trying to fit the GNU logo in there. I'm not very good at using image manipulation tools, but it looks pretty good. I realized I had to learn about layers. And this project is sponsored by Open Source Security and Embecosm. So you'll be hearing a little bit more about them as well. And there'll be some useful links and information in these slides that hopefully we can share the slides with everyone after this, that people might want to have some deep dive into some of the information we might be discussing. So yeah, hopefully there's a way to share them after the fact. So who are we? My name's Philip Herron, as I mentioned. I'm the lead maintainer for the Rust-GCC front end. I have a Twitter, and I'm based in Belfast, Northern Ireland. And then Arthur, do you want to say a little about yourself?
Yeah, well, my name is Arthur Cohen. I'm a French engineering student and now a compiler engineer at Embecosm. I also have a Twitter, and I also have a cute dog. And yeah, I've been working on the project full time for 3 months now since I got hired.
Yep. You've had an interesting journey into it as well, since you were a Google Summer of Code student last year, so then we ended up hiring you.
Exactly.
So summary, usual. What is this? As I said, like, what is this thing? What are our motivations? What is the project status? Oh, someone says I'm just seeing a black screen still with the occasional emoji. Hopefully people can see the slides still.
I can see the slide.
Okay.
You shouldn't be seeing a black screen.
Can anyone else confirm oh, it's still it's black for them as well?
What
if I go out of full screen?
Oh, someone else can see it. Yeah.
I'm using Google Chrome. I've had issues with video stuff in Firefox. Maybe it's worth trying another browser. Well, I'll continue going then, assuming that people can actually see the slides. So yeah, what is this? The motivations, project status. Where are we? I thought it might be interesting to go into some of the technical bits and pieces that we've been working on from a compiler perspective. It's an interesting journey going into the nitty gritty of a language and trying to figure it out. From that perspective of actually implementing the language, so I think there's some interesting things to talk about. This isn't just all of them, but we're just going to do a nice high level overview of some of the interesting bits and pieces. I think another important aspect is to talk about the community and how you can also get involved. Obviously this is an open source project. It's on GitHub. We'll be sharing you all the links and how to get involved and everything there towards the end of the talk. Obviously, feel free to ask questions throughout. We'll try our best. Hopefully Arthur can interrupt me and I'll interrupt Arthur, vice versa, through the talk if something happens or there's a pertinent question. But obviously we'll leave time at the end for that as well. So what is Rust-GCC? It's a full implementation of Rust on top of the GNU toolchain. It's a project that originally was started back in 2014. I was around, I think it was PyCon 2013 or something like that. And I heard of Rust for the first time. And it was a really cool project. The thing I really loved about it was the match expression. I think that made my first project in Rust was actually writing a Lisp parser, just because it's a nice simple thing to start and to try and implement. And I just thought, well, actually, that made the lexer really, really beautiful to look at, having a match expression. And so I kind of fell in love with the idea of the language. You know, it's a native language. I really like native languages. I think there's a lot of benefits there. And overall, I was just really interested in it. But one of the problems I had was back in 2014, there was a lot of language changes. How you actually allocated memory was pretty complicated back then. There was all sorts of little interesting pieces of syntax used, like using tilde, ampersand, you know, and the @ symbol were all interesting things that you could combine in strange and interesting ways. And like I think at one point they even tried to bring in a garbage collector and all sorts. So I tried to start keeping up with the language. I couldn't quite keep up with it at all. So eventually I kind of thought, well, let's just leave it for a while until they release. And so we left the project, and then I was really interested. I love working on compilers, so I revived the project back in 2019 as a spare time project. And over time, I was then, after making some more progress, was contacted by Brad from Open Source Security, who was interested in the project, and he ended up funding me full time to work on this, along with Embecosm. And so right now where we stand is we actually have 2 full-time engineers, so that's why it's me and Arthur. So we're both working on this full-time right now. So yeah, maybe you're already familiar with the GNU toolchain, but it's an open source compiler toolchain, including assemblers and linkers and all of that sort of stuff. So I'll just go over a little bit of the motivations. There's a little bit more of a detailed explanation here if you want to look at our frequently asked questions. But the idea here is we want to be fully upstream with mainline GCC, so then that any downstream GCC trees can actually just get Rust support, you know, by just fetching the latest changes. You get the front end for free. You know, we want a reusable GNU toolchain, as I said, so that means we're using all the existing tools like assemblers and linkers and debuggers. We want to reuse the standard libraries from Rust, so we don't want to like write our own standard library there. It doesn't really make much sense. That's a lot of effort that we don't really need to do. We might as well just reuse them. But I think a lot of the motivations from a commercial perspective or from the people who fund us were really interested in GCC plugin support, including LTO and control flow integrity. So there's a lot of open questions there if you're going to start mixing languages. So if you're going to have a C and C++ project and start adopting Rust, you want to make sure you still get link time optimized code the way you expect. You don't want to because it could be seen as a net negative if you don't have these tools. If you're starting to, from a security perspective, mix these languages. But something that a lot of people are interested in as well is, you can drive the adoption of Rust, so we can backport this front end. So currently we're working in GCC, like, we're pretty close to the master all the time. We do merge from upstream pretty regularly, usually every month or so. But like, if the idea would be once we're merged upstream, we could continue to try and backport the front end so that, older versions of GCC then get Rust front ends. So you get Rust support on different versions of GC, which seems to be of interest to people. We obviously aren't working on that right now, but it's an interesting motivation down the line. But as I said, feel free to look at the frequently asked questions. There's a little bit more detail in there, and obviously feel free to ask us questions about that as well. So project overview. I thought this was an interesting way to sort of give a high-level overview of where we are. And so currently, whenever I was doing this project full time, we needed a way to split up the project into key milestones as a way to make sure the invested parties could track the project, make sure the funding's allocated correctly, and there's progress being made. So the best way I could think of doing this was if we split up the project into different key things. So like core data structures was the first thing we worked on, and it, obviously I was finished at the start of like last year. So that was all about, can you define a structure? Can we set up the inference variables? Can we do some type inferencing? Do we have all our built-in types that we expect, like arrays or pointers? All that sort of built-in, really primitive basic stuff. And so yeah, that went well. It was kind of the real core. You can't really do much in a compiler unless you can actually set and create a variable and start doing some basic type checking and all that sort of stuff. Control flow 1 was all about, all right, can we define a function? Can we call a function? Can we have a loop? Can we have if statements, all that sort of stuff. So that's then starting to do some basic control flow, so we do some more interesting programs and some more interesting test cases to make sure we're on the right track. But my main investment here was that I want to spend a lot of time on getting generics and traits. These are the two major pieces of Rust that I was pretty worried about. I think it's a pretty complex piece of the Rust language, and so getting it right was pretty critical. But as you'll see later on in our talk, sometimes you can't. It's whenever you're writing a programming language, you want to test everything in conjunction with one another. You can write a feature, but really what you want is this feature talking to this feature and seeing what happens when they interact. And sometimes you get interesting results. And by interesting, I mean wrong. So yeah, we did our best as we could with generics, but really, you have to do generics before you do traits, because traits require some implicit type parameters. So you need generics before you can even attempt it. And so that was then exposing more bugs in generics because it's used in a very specific way with implicit type parameters, so it gets kind of awkward. But then that was helpful. And then from there on, we went on to look at some more control flow, which is to do with pattern matching, which is maybe not the correct title for that one, but there's still more work to do in our pattern matching. But there was an awful lot more work there with how you do auto deref, and method resolution was a pretty core one there, because method resolution is pretty complex in Rust. It just kind of deserves its own full 1 hour talk, and I still don't know if you'll get through how complicated it can be. It's very powerful. Complicated is probably the wrong word to use. It's just very powerful, but it's pretty cool as well. So we've done that. So that brings us up to December of last year. So that was quite a lot of work done last year. And so where are we now? So from that time in December, we were working on macros up until the end of March. And this is in that time we hired Arthur. So obviously the first thing I did was, here, take over macros for me, and please do that. I don't know enough about macros. No, Arthur did a great job. He took the lead on that, and it's really nice that he was able to stamp his name on this particular feature. So he knows it inside out, and he's going to talk to you a little bit about that in the next set of slides. Obviously, right now, we're pretty focused on imports and visibility. So what does that mean? That means, like in the compiler, can you actually import code? But it also means, can you link against other crates, but also can you do privacy checking? So if you have a private member within a module and you're calling it from a completely other module, are you allowed to do that? And so in Rust, it's a little bit more complicated than public and private, like you might see in other languages. You have to you resolve it within particular paths. And so we're working through that right now. So it's a pretty key one. We're really hoping that after we get this milestone out of the way, that we could potentially start really focusing pretty core on getting libcore working. So we'll talk a little bit about that later on as well. We'll talk a little bit about const generics. That's a pretty new feature, and there's a little bit of a reference to that later on as well. And talking about that. Intrinsics and built-ins. Intrinsics and built-ins are something you're always doing. There's quite a lot of built-ins. There could be built-in macros. There's what's a good built-in macro like concat or something, or there's built-in functions like your atomic fences and atomic barriers, atomic add, atomic, all those sorts of things are all built-ins and intrinsics. So they take a while. A lot of them are quite simple. They're good first PRs for people to get involved in the project to implement them, but there's quite a lot of them, and so we only really add them as we need them at the moment, but we do really need to spend probably the guts of a month just focusing on getting them done at some point. And obviously borrow checking, we need to plan it in properly. We're sort of treating it as a side project at the moment, and Arthur will be talking to you about that as well. And as I mentioned, this milestone table is as of the 2nd of May this month. So we have a reporting repository, so you can always go and view this repository. I think I have it open over here. So we have this repository and we upload a report every week, and you can always see that. And we always like to shout out to different contributors in there, some of which I think are already in the chat, which is quite cool. Like for instance, Mark Pulis he's the one who did a lot on imports and visibility last year. He ended up implementing our module support, which is pretty cool. So it's been a really great project. And so, yeah, now I'm going to hand it over to Arthur, and he's going to talk about his dog and talk to us about a little bit about macros.
So yeah, this is my dog. His name is Jinko. He's 7 years old. He's the kindest dog you'll ever meet. And we thought we'd use this picture as a sort of transition between the different parts where Philip and I are speaking so that we could get our chickens in order. So yeah, I'm going to tell you a little bit about macros. As you may know, there are macros in Rust which are sort of similar to the macros that you could find in C using the preprocessor. You can consider them as a separate language which is baked inside the language. So they are executed at compile time and their content is replaced, like their expanded version is replaced during compilation. They are much more powerful than the macros that you might be using in C. They're also more hygienic, and we'll see what that means, and they're also much more safe. So if we look at the first example, this is something you might have seen already, and if you got some experience writing C macros, you might spot an issue right away. But actually doing this sort of macro where you don't take good care of adding parentheses around your parameters, you could sometimes have surprises because of operator precedence. So for example, here you'd expect that 2 times 2 plus 2 would be equal to 8, 2 times 4. But actually, if you print that result, you'll see it's equal to 6. However, if you do the exact same macro in Rust, you'll realize that the result is actually equal to 8, because you're not just copy pasting tokens at the source code level, you're actually operating at the AST level. So what you're doing is piecing together new little bits and pieces of AST called AST fragments and adding that together. So here we're actually just multiplying 2 and the arithmetic operation of 2 plus 2. So the operator priority is respected. Another example of what you might have wanted to do in C is using these kinds of variadic macros. So you can either do that using via args, for example, but it gets a bit complicated. Or you could also think about doing something like max1, max2, max5 for that last line, and have different macros with different sort of dispatch levels, which get expanded properly. But it gets really hard to maintain. It's hard to read, and it takes a lot of space. If you look at how we do that in Rust, you can see that a single macro may have multiple matchers, so multiple ways to get invoked. And you can also realize that on that third invocation line, we're actually using repetitions and calling the max macro recursively. So if we look at the first matcher, which is simply returning, like the first match arm, we're simply returning the value. Max of the value is always that value. The max of 2 values is the greater of those values. And if we have more of these values, we'll simply recursively call the max macro until we get the maximum of the remaining part, sort of. And all of this gets expanded at compile time and gets inserted in optimized later on. So this was a really interesting challenge, and it actually took a lot of algorithm and figuring out how to do. For example, repetitions were super hard to understand, but they were really interesting. And if we go to the next slide, you can see that it says that sometimes macros are not even necessary. And what I was thinking about is that, for example, if you look at the hardware abstraction level from ST, you'll see a lot of macros regarding GPIOs, so pins or ports and all those sorts of stuff. But in Rust, you can actually avoid using that because of the very, very strong type system. So what's actually done, for example, in the Rust equivalent of the hardware abstraction level is that the different pins that you can use with various ports are restricted at the type system level. So for example, you won't be able to use the B13 pin if there's no 13th pin on the B port, stuff like that. And finally, Greenspan's 10th rule tells us that any project that gets big enough will inevitably end up re-implementing a subset of Lisp in the macro system. And that's something that you see in a lot of C projects. And if you wish to do that in Rust, you can do it even better, I want to say, because it's really, really easy to do some very complex parsing in macros and have domain-specific language like you would find in very high-level functional languages such as Scala or Haskell. And you can do that in Rust and still have it compile natively. So yeah. You're muted, Philip.
Whoops. Yeah, thanks for that, Arthur. I really appreciated you doing macros. I realized when I'm in my own Rust projects, I never really use macros that much, but they are actually really powerful, and you should use them because they're the coolest part is actually just that they're typed. So from the get-go, you're getting a lot of checks for you. It's not just raw tokens. You can pass in. Oh, I expect that this should be a type AST, not just an expression.
There's a question in chat. Does Rust have a macro that generates compile time function, like generating the max function and running it directly to have the value computed at compile time? Yeah, I feel like that's possible, but that's not possible for us because the context milestone is not there yet.
Yeah, so our I'll talk to you a little bit about the const generics. There's a couple of bits there. So what you're talking about there is more about constant evaluation, like const expr from C++, and we do need to do that. There's a little bit of it there, but it's very basic at the moment. It doesn't handle very much, but yeah, we're going to have that working. And I'll talk a little bit more about that a couple of slides. And so I thought I might talk to you a little bit about something I've been working on lately, which is slices. There's some really interesting bits and pieces from a compiler perspective here for something a lot of people might take for granted. There's some really interesting design decisions taken here from in the Rust language. So I think I want to talk to you about that. So I want to talk to you about what is a slice. It's worth just noting that it's definitely not a slice of pizza. Why is this interesting, and what problems did we have? And this last point about Rust 1.49 versus 1.50, that's important. It references the question that I just got asked about const generics and const expressions, and it kind of references back to our milestone table at the start as well. So we'll be talking about a few different things here. There's an awful lot more problems that we encountered, but yeah, we'll get to it. So what is a slice? So a lot of people might be familiar with slices from things like Python or Go. They're pretty common things these days. Really what you're talking about here is, I've got a contiguous piece of memory, and the most common example you're ever going to see about this sort of thing is that I've got an array, and I only care about a couple of the elements in that array. So I'll create a slice. And so the syntax for that in Rust is let be, and you got this 1.3. So you're saying I want this range of values in that array. And so really what you end up with, and like from a C perspective, would be like a fat pointer. I've got a data pointer to this offset of this array. and you're offsetting it by the start of your range of 1. So this might be familiar to people from a C background, but if it isn't, it's not really that important. What I want to show here is more about some of the issues we hit and how we sort of dealt with them. So hopefully some of this makes sense, and you're used to seeing pointers and offsetting pointers, but don't worry if you're not. So what I want to talk about, like, why is this interesting? So I think from my perspective and prior perspective is slices are actually implemented purely in Rust code. A lot of times in other languages, the compiler will just generate code for you to do this. But actually, the cool thing here, it's we're actually testing the compiler quite heavily by compiling the code that is required to generate a slice. And the code that's responsible for that is in libcore. It's a real goal for us. If you can compile libcore, you can pretty much compile a lot of Rust programs at that point. So that's what we're really chasing at this moment. And it's the libcore gives a lot more primitives than you would actually think, and you'll see an example of that in the next slide. It's a lot more important than you could ever consider. It's really highly generic code. So as I mentioned before, it's whenever you start combining your features together, that's when you start finding more and more issues, So when we did generics, it was all about generic structs and some generic functions. But then when you start mixing that with generic traits and hierarchic trait bounds and things like that, where then you start hitting more complex issues that you need to think about. So this has been interesting for us, bug perspective. It also required us to start thinking about this thing called lang items, which you'll see as well. And this notion of dynamically sized types is something we've only figured out very recently, and thanks to Arthur for figuring it out. So what problems did we have? As I mentioned before, auto deref was method resolution is what I really mean by that. I'll not go into that one in this talk because it's too much time required for that. But I'll talk a little bit about operator overloads, because this is sort of the mechanism that sort of drives this piece of code. Talk about unsized coercions as well. I only mentioned generic monomorphization because, as I said there a second ago, it's whenever you talk about generics and how they interact with other features, that's when you start finding more and more bugs. And monomorphization, it's a fancy term of, like, in C++, you might be familiar with creating a template and you substitute it with a particular type. In Rust, you can do an awful lot more. It's a lot more powerful. So that kind of deserves another set of slides in itself. But what we hit there was just more bugs. So it was great to hit more bugs early on. And as I said, I want to talk about the dynamically sized types, which is a pretty interesting design decision taken by the Rust language. And we'll talk about that as well. So lang items. So what is a lang item? So there's a couple of things to talk about this slide. Probably the first thing that's worth mentioning is this is actually from libcore. It's actually hidden in a bit of a macro, but actually you can see here that adding integers is a lang item, and it has an impl block, and it is defined in libcore. So it is quite surprising how intrinsic core is to the Rust language. It actually needs this core library to know how to add numbers together. It's like I don't know of any other language that needs this. But really, what we really mean is that obviously your code doesn't generate function calls to add numbers together. This adds an awful lot more information to the type system about what you're doing, and it keeps things consistent. So if you want to create an add implementation for any custom type, it's all you have to do is add an impl block for that type. And so it's worth mentioning that if I go back, I've got a compiler explorer here, showing like what this means. So, and some of you might be used to compiler explorer, but we've got this example for here's the add trait, and it's got this notation of a lang item, and the lang item is a way of marking a particular item in your code, such as this trait, with a particular tag called add. So we know in the compiler that, all right, we've got this long expression that we know we can there's a particular way to add it, and there's a particular function for it, and that we respect the function. So we can actually put like a printf in here to make sure we actually do hit the function correctly. And so yes, you can actually play with GCRS on Compiler Explorer. So what I want to show here is there's the compiler down here. So you can select GCRS snapshots. Obviously, don't be expecting to throw in a lot of complicated code in here because we don't have libcore here. You have, if you want to use a lot of features, you're going to need to pull in the libcore code yourself, which takes time. But what I want to show here is the fact that in this add expression here, it is actually generating function calls. But obviously, if you turn on optimizations, you'll see the assembly, it goes away. It's just inlining everything for us. So yeah, it's just cool that these things are defined in the core library and pure Rust code. And so the next one I thought I'd show is range. So what I'm trying to show here with these slides is how the picture builds up a little bit for how we actually generate a slice. So this will all make sense in a few slides from now. So just bear with it. So range is even a lang item. And so this whole notion of let a equals 1.3, this is actually just syntactic sugar for constructing this this particular structure. So that's all that is. There's a compiler explorer for that as well. So yeah, range is just a struct. The next one that's worth talking about is the index trait. So you see here, there's going to be a picture building up here. So here's a funny example. I'll maybe just go to the compiler explorer. It might be better. So we can see here, we've got an index lang item, and what this index lang item is all about saying, well, we can have an operator overload for any struct we want. So when you use array index expressions like here, a square bracket 0, this is an array index expression. We can actually have an impl for index on our tuple struct foo, and it's a bit silly. Like obviously you can just in Rust you can do a.0 and a.1, but I'm just trying to illustrate the point that actually you can implement the index operation. This is quite a Python thing to do, creating all the operator overloads to make your types look like just look like normal data, and the compiler takes care of everything for you. So yeah, so obviously the argument here is of a size. So the index trait takes a template parameter, which is what your index type is going to be, and so that's how that all gets figured out as well. And so we're actually just instead of addressing the structure here, we're addressing it by index expressions. So yeah, it's building up a picture, as I said. And so here's how the picture builds up. So we've seen how we create the range objects by using 1.3. So that was syntactic sugar for just creating a struct. We've seen that we can do operator overloading for any type we care about. And so in this case, the function that's responsible for actually creating the slice here is this little piece of code here. So we're implementing index for slice. So that's a bit confusing because obviously we have an array here. So a doesn't map to this function. So you wouldn't think that self is actually going to be passed here correctly, but actually it does. So this is another piece of this is an unsized coercion. It's called. It's a piece of auto-deref. It's a piece of Rust code it's fairly confusing when you first see it because it doesn't make much sense, but actually it does. So if we go back to the compiler explorer, we'll see here that in this line, as we see, we create the range objects start and end 1 and 3, and then we're doing something funny here with the array. What we're actually doing is creating a slice directly in as an adjustment. So we're creating a slice of saying here's the array and it's a capacity 5 and passing that directly into the function itself. So what I quite like here is by looking at the Gimple IR and GC, it's very C-like. You can kind of see quite strongly what's going on in the language. So you don't necessarily have to be looking at your assembly here. It's quite complicated to follow assembly, but following the Gimple is quite nice because it follows very closely to what's actually happening. Obviously, when you turn optimizations on or off, it doesn't affect the Gimple. The Gimple is just the Gimple. So yeah. But going back to the slide, if I slideshow again, as I said, this array is actually turned directly into a slice for us so that it can be passed in as self. So it doesn't look like these might relate to each other, but they do. So these are some of the things that you end up finding from a compiler perspective. You have to be careful of, because when this really just gets turned into a method call of, turn A into a slice and then call it with this range object. And then all of this is all very generic, so yeah. So the template parameter I is actually ends up being, the range object T is the type of the array, so it actually is an I32 because it's, the type of this generic slice. So yeah, it's quite a lot going on in that function than really meets the eye. And the final thing it's worth just mentioning that really threw us this week, we almost have a patch that fixes this. Usually in embedded programming, the size of a pointer is just the same. It doesn't really necessarily matter what the pointer points to. The pointer is just a pointer. That's not necessarily the case in Rust, which really threw us. So as you can see here, that you can actually assert that a pointer to a slice in Rust, which is denoted by these two square brackets, is actually of 16 bytes. A pointer just to a normal integer is 8 bytes. And so that seems confusing. So what we're really saying is the type layout of this slice pointer is completely different to any other pointer. And that is a strange one, but it is actually documented and there's a reason for it. And it is actually just a special case, and it's called dynamically sized types. So it's only this very specific case where you have a pointer to a slice that this is actually happening, and there's a reason for it, so that we can pass around these slices without giving references to stack allocated structures. So it just sort of magically works. There's I could go into detail where it actually really hurt us. Where it was like I had all this code working, but we ended up returning stack memory. But it's actually, once you realize that this is actually a completely different type layout, it just magically works. It's really cool. But yeah, it took a while. It took Arthur to actually read the documentation, which I didn't. There's a whole comment in the code called slice from raw parts. There's a whole safety comment there that I should have just read more deeply, and I don't know, just let it slip past me. And yeah, I'll talk a little bit about const-generics. So the reason we've been focusing quite strongly on Rust 1.49, because in Rust 1.50, that's when const-generics were introduced. So do you remember in that slide I mentioned where the array was directly turned into a slice? This is now completely changed since 1.50. So you can actually, this is the same impl block, but actually it's for a generic array. And so in this case, you actually can now support in Rust this notion of const generics. And so here we have a const n, which is so that we can have a const array capacity. So this means we can match this impl without you still actually do need the unsized coercion, but the way you method resolve this is completely different because of this this array notation here using the const generic. So yeah, we actually are blocked starting looking at code after that point because we need const generics is what I mean. But everything else is looking quite good. And so in const generics, it kind of breaks down into a few different pieces that we need to do. We need to support the grammar. The grammar has changed here. So generic parameters here. We used to just say, well, T and I will are generic parameter, but now this whole notion of that you can have a const keyword here. So we need to support that in the grammar and the AST. And then we also need to support our constant expression evaluation. So obviously GCC will optimize your code whenever you just have 1 + 2 + 3, it'll optimize that and turn it into whatever. But actually sometimes we need to be able to constantly evaluate these regardless of optimization level, which is what you see in C++, the whole const expr keyword. That's what that's all about. So we're actually very, very lucky that we're tightly integrated with GCC here, because we can actually just reuse the code from the C++ front end to do that for us. It maps over very well for us, because writing your own constant evaluation code, it would be pretty tough. And C++ seems to work, so we'll reuse that, I think. And so, yeah, I'm going to hand back over to Arthur. It's a little bit of a whirlwind on slices. I just wanted to put across some of the interesting bits and pieces that we hit, and hopefully it was interesting.
So yeah, the next thing we wanted to talk about is borrow checking, which is something that if you know Rust, you might have encountered already. There's this running story about how you always fight the borrow checker when you learn Rust. And so I'd like to speak a little bit about what's borrow checking and what are the problems that this particular concept solves. So for that, we're going to look at an example in C. On the next slide, which is about like 2 pointers. So this example, basically, it's taken directly from the Rust book, so there's no credit for me on that. What we actually do is that if the input is superior to 10, we assign 1 to the output, and then if that input is also superior to 5, we multiply that output by 2. So what we can see is that we can easily assume that output will always be 2 if the input is greater than 10, because something greater than 10 implies something greater than 5. And that's something that a compiler can see easily and optimize. So for example, we could do this instead, which would be caching the input and only dereferencing it once, keeping it in a register, and then accessing it super fast. And actually then just check if the cached input is superior to 10, we can just directly assign it to 2. And otherwise, if it's just superior to 5 but inferior to 10, multiply it by 2. And if you take these two versions and actually run them one against each other, just this is what we're doing, but what we're doing is we're actually being a little tricky with the function, sorry, in that we're giving the same pointer for input and output. And you can see that the results are that after 10, actually the results are completely different, because this is something called aliasing, which means that basically because the 2 pointers alias and point to the same area of memory. Yeah, sorry, but there's the sound from my CEO who is in the same row as me. So if it's too bothering, I can move. But yeah, actually, you get completely different results because, yeah, the compiler is not allowed to make that optimization in C because the 2 pointers might point to the same area of memory. And so that would actually be an aliasing violation. And so if we look at the same code in Rust, so this is the exact same function, and we're just trying to give it, again, the same, a pointer or a reference to A and a mutable reference to A. And actually, you'll notice that the compiler does not accept that input and errors out. And this is one of the functions of the borrow checker. And this means that, for example, for embedded context, it can actually optimize your code in that regard as well. So this is an optimization that the Rust compiler is allowed to make, that almost no other language is allowed to make. Something else that we can think is something else that we can see is that, for example, if you were to do this kind of stuff, which is very basic, it's you're just creating an array on the stack and then returning it, like the address of that array. So when you return from the function, the stack frame is popped and your pointer does not point to anything correct anymore. And actually, this is something that happened at my last internship, where another intern added that in his merge request, and the senior engineer reviewing him merged this to master. And this caused our CI to be broken for 5 days until someone took the time and investigated it. And if we were to do the exact same thing in Rust, once again, we'd get a nice error. So here what we're doing is that we're creating a string. So this is a dynamically allocated string and returning an address to it. And that's what the compiler tells us. So the compiler says that, yeah, we're returning a reference to data that's owned by the current function. So once again, this is something that the borrow checker prevents, as well as many other common issues like that, such as double freeze or data races. And the slides after are to show you that if you really want to do some undefined behavior because you really miss your C undefined behavior, what you can do is returning row pointers and then using the unsafe keyword, dereference as that row pointer, and then create a nice little segfault as you would have in C. So what's the plan for us to add borrow checking to gccrs? First of all, this is a very, very complicated topic, and it's extremely complicated algorithms that neither Philip nor I are able to understand or implement. The feature is extremely complicated. It would take us usually a month or maybe years to implement, and there would probably be a lot of subtle differences with the existing borrow checker, which is present in rustc. So one of the possibilities that we have is to actually integrate with the community and utilize the efforts made by the Rust community to formalize and develop a new borrow checker called Polonius. So this is our current pipeline in the compiler. We have an AST and abstract syntax tree, which is built from parsing Rust code. We lower that AST into HIR, which we type check into a typed HIR, and then that typed HIR is given to the backend of the compiler. What we plan on doing is actually to integrate with a Rust library called Polonius Engine, which implements the rules of the borrow checker. And to do that, we'll write a little bit of Rust code to interact between our C++ compiler and the Rust library and pass information together. And one of the issues with borrow checking is that how do we get borrow checking in a compiler that cannot compile Rust? Like, how do we compile a Rust library with our like, how do we get our Rust compiler to ship with a compiled Rust library when we can't compile Rust without a borrow checker? So, because borrow checking is such an integral part of the language, it should never be disabled, and users should never be able to compile Rust code without it running through the borrow checker. Similarly to how you don't want a user to compile your code without running through the type checking phase. So what we're going to do for this is that we're actually going to create a stage 1 compiler, which is a very basic, not optimized, and not completely functional compiler, but that can still compile Rust code, use that to compile the Polonius library and our FFI, so for instruction integration, sorry, and our FFI layer, and then use that to compile a stage 2 compiler, which can only ship with Polonius and with the borrow checker enabled at all times. And so the end user will never see the stage 1 compiler because, I mean, first of all, the compiler on your system is currently bootstrapped and you never saw the stage 1 compiler. And because, yeah, we don't want you to be able to do some non-Rust stuff with our Rust compiler.
Yeah, I think it's been a question that's come up with us for quite a while, and it was a hard question to answer about the borrow checker because we're so focused on compiling Rust code. One of the things is, like, you know, technically you can argue that, you know, we don't need a borrow checker to compile Rust code, but we don't really want to start introducing these sorts of inconsistencies. I think it's pretty clear the community doesn't want that. So yeah, we have to make sure we have this bootstrap process that Arthur's figured out for us. So I really appreciate you putting the work in to figure that out. And so I thought it might be nice to move on to the community. And so whenever I started this project full time, obviously I started realizing, wow, compilers are pretty hard. Inference variables were pretty complicated. You know, a lot of people, I think, misconceive that Rust is just sort of like a fancier functional C++, but the type system is just so different. And so I remember at the time I was fighting with inference variables, and I just was having a bad time, and I just kept writing in my comments, you know, in my printf statements, compilers are hard 1, compilers are hard 2, to try and trace my code. So that's where that slogan comes from. And so I ended up creating a bunch of bugs. So people who've been you know, contributing code, I've sent them out a bug to say thank you so much for contributing to the project. I really appreciate everyone that has been involved in this project. You know, I couldn't do it without everyone. It's been sort of my dream to always work on a front end for GCC, so it's been a great couple of years. So getting involved, I thought it might be nice to talk a little bit about that. So my goal is to make working on compilers fun. Like, I was doing this in my spare time until a year and a half ago. You know, I forget what year it is anymore because COVID makes time work funny. I don't know. I can't remember. But yeah, I've been working on this full time for a year and a half, I think, and it's been fantastic. And we've been trying to make compilers fun, so we've got actually a whole bunch of what we label as good first PR issues for the community, for new contributors who are interested. We try to make them with guides, so that you can follow the code where we think you're going to need to make changes, what type of change you're going to make, but not all contributions need to be code. So, for instance, you can always raise bug reports. So we really appreciate it when people go into Compiler Explorer and try different things. Maybe they'll probably find an ice. They'll find hitting some assertions or just crashes or whatever. It's just really worthwhile spending your time. If you do hit anything, we don't really care how insignificant. Just raise an issue. We'll look at it. We also like to leave. Well, I like to leave a lot of some like refactoring cleanup work as good first PRs. I always think refactoring work is something obviously we could do, but I think it's also a great way for people to get involved in the compiler, because you sort of get familiar with the code and how it's structured without really worrying about, oh, I'm changing how this trait works or something. You know what I mean? So there's a lot of scope to make your mark on the compiler. So many people have, it's been fantastic, Obviously, we were part of Google Summer Code last year, and we're part of Google Summer Code this year. So we're hoping we're going to get some students this year. So there was some applications made, and we were happy with them, and we hope that we'll hear information about that soon. And Arthur made his journey through Google Summer Code, and I think you enjoyed it.
Yeah, it was really, really cool. The mentor was super nice. And the work was extremely fun.
And so you worked on Cargo?
Yeah, Cargo gccrs. So this is our wrapper to integrate tightly with the Rust build system, which is called Cargo. And basically the idea is to look at the arguments, the different arguments passed to rustc compiler, and then also translate them into arguments that our compiler can understand, so that we can mimic the behavior from Rust as much as we can.
Yeah. Well, that's an interesting question about the Cherry support. There's a few things to say about it internally at Embecosm. I know there's work to add Cherry support for Rust on LLVM, I think, or there's something around that going on right now. As far as I'm aware, if the GC Midland gets support for Cherry, we do get a lot of this for free. There will be some slight tweaks from what I've read about Cherry support in Rust. I think there's some slight tweaks that need to be made to the core library, especially around, as I mentioned, that dynamically sized type where the pointer was like, for that slice case was completely different type layout. I think there's some subtle things there that need to be tweaked, but I don't know the full details on that. But in theory, we get it for free. So potentially the compiler doesn't change, but the core library does, if you know what I mean. So that's kind of cool if that works out the way we hope it does. The other thing is worth mentioning, as I said at the start, we do a lot of status reporting. So I think we put a lot of work into our reports. It does take quite a lot of our time, but I think it's been worthwhile. I'll maybe just quickly show you what that looks like. As I've shown you the reporting repository, we do weekly and monthly ones. The weeklies are smaller, but the monthly is like a concatenation of what was done in the previous weeks for that month. So it combines everything, but it has a nice TLDR of like, what did we do? Why did we do it? Talking about, we have a community call coming up, talking about our testing project, which Arthur can talk about in the next slide, all the different completed activities. But the thing I really like to bring attention to is some about new contributors this month and talk about what they did, why they did it, and link to them directly. I really want to shout out to that as much as possible. And so you can see here, like, there was this issue fixed by David Faust, and he, here's the information about the issue he fixed. There's all sorts of things here. Like there's a bunch of stuff that Arthur fixed in macros, and we encourage people who want to get involved to write their section if they want. And for me, having these reports and all these detailed change logs of what's been going on I'm kind of hoping sort of serves down the line as some sort of starting point to show how you could actually build a Rust compiler from the ground up, because we've got the reports there where we started and what issues we hit. So I think it would be kind of interesting to see, for people to see how it layers up. I always sort of think it's a bit like building a house. You can't start building a house with by the roof. You need to build the foundations and all that sort of stuff. I find the layering up process interesting. And so, yeah, that's our status point. We do a monthly community call. We have that actually back to our old time slot of the 9 o'clock UTC, because most of our contributors are in Europe at this point. There are some in America, so we're actually going to be starting a second community call, I think on a Wednesday. We haven't announced it yet, but the community call is actually open to anyone who wants to join. It's not just for people who are directly involved in writing code. Like, it's not just for me and Arthur. This is for anyone who's interested in the project to ask questions. We talk about what we're doing as a round the robin, what did you work on, blah, 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 what issues did you face? We also want to leave it in such a way that if you want to join and just listen, you don't need to put on your webcam, you don't need to put your mic on, you can just listen. That's completely fine with us. It's hosted on Jitsi, which is like a free and open platform. You don't even need to create an account. You can just click a link and there you are. You're set up and spying on us. And so we announced the monthly community call is always going to be this time now for this, but there will be a second one announced for a different time zone, which was looking likely to be like 1800 hours UTC on a Wednesday, probably the second or third Wednesday of the month. I can't decide. So yeah. We'll talk a little bit about the future work. So I think I'll leave it to Arthur to talk about our testing project. He's done a lot of work there. So yeah.
Yeah. I'm going to run through that a little bit quickly because we're running out of time.
Okay.
But yeah, we have a big testing project, which is in a separate repository. And the idea is to add multiple interesting test cases that do not specifically make sense to be tested directly through the compiler. So for example, we're running on the entire rustc test suite. We're also running on some projects, such as a cryptography project called a cryptography algorithm called LEE3. We're also trying to follow our progress through compiling libcore. We're running a parsing test suite. And in total, this testing project contains around 24,000 tests. And it's just a very helpful metric for us to run through every month and pause the progress and automate and see regressions as we go through the different milestones.
Yeah, it's been pretty cool. We even run the rustc compiler on our test suite, which is kind of funny.
Yeah, right. I forgot to mention that, to make sure that our test suite actually contains valid Rust code and we're not in completely wrong direction.
We have a funny issue there, actually. The Rust compiler fails in our execution tests because our main function returns an integer, but that's not really allowed in the Rust compiler because they have this notion of a main shim, which we will be doing as part of the current milestone we're doing, but it just was not super important until now. You will talk about your test runner, Arthur, for the testing project?
It's just, you can find it on the repo. It's just a very simple script that's heavily multi-threaded so that we can run the 24,000 tests in like a regular time that we can handle.
It's written in Rust as well, which is pretty cool. We also, obviously, we have a test suite directly in the compiler, but this test suite is much more about like language tests. So they're quite small test cases some of the times. They're quite focused. Some of the test cases are literally called like issue-1234.rs, to link back to GitHub issue numbers, which is quite nice to have that level of, what's the right word? Not transparency, but auditing, or something. It links back so you can follow the whole history of what went wrong with that issue, which is pretty cool. And obviously, the testing project, my long-term vision down the line when unicorns exist and this is all working, that I think it would be really cool to compare and contrast the two compilers of rustc and gccrs, because obviously, I know there's new websites like Phoronix.com always like comparing LLVM and GCC, and they talk about energy efficiency and stuff like that. I think that would be really, really neat. just out of curiosity, because Rust is such a modern new approach to a lot of things, and it's just really cool. We also are pretty interested in language standardization. You know, we've had to figure out a lot of stuff ourselves. The Rust is pretty well documented. There are parts of it I don't think are documented well enough, especially around method resolution. There are things I do feel are work because of the implementation, rather because they're intended to behave that way. You know, this is really nitpicky stuff, but I think, you know, standardization of a language is important, in my opinion. And everyone has their own opinion on that, but we're also interested in creator runs as well. I think it sort of directly relates to what we're sort of doing with the testing project right now, but the idea is the creator runs will be running our compiler against, you know, all sort of crates in the ecosystem to try and see what level of compatibility we have. That's something we'll be doing down the line at some point. I think would be pretty interesting. And obviously bar checking, as Arthur talked about, we still need to do all of that. We're just very focused on getting libcore working at this point, and seeing where we are, and actually just compiling Rust code without a bar checker and seeing how that looks, and getting that working well. Because once that's working well, you know, you can compile Rust code, but, you know, you do need the bar checker before we can release it or anything like that. And here's some links. We've probably posted some of these links in the chat as we went. We have our GitHub project. We have a reporting repository. You can always email me. We have a Zulip server, which is feel free to anyone. We're on IRC, and we have a mailing list. All the usual suspects there. But I think the main thing I want to say is, you know, special thanks to the people who sponsor our project. So that's Brad at Open Source Security. He's on Twitter. You know, there's Jeremy at Embecosm and David Edelson, who brought this together for us to be working on this full time. You know, so I'm very, 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 very grateful to all these people. And obviously, you know, we're always seeking partners if we want to get involved in this project. You know, we believe that Rust should have a, you know, a GCC front end. You know, so if you want to get involved, you know, please contact us or me. Or if you want to be a contributor, we are happy to mentor people. It's a really great, you know, piece of experience to get, you know, to have in your CV or on your GitHub profile. So please feel free to contact us. We're there to help you, and because when you write code for us, it helps us as well.
Exactly.
There we go.